que eu vi no FOSForums lá. E aí, tudo bom?
Deu certo, né?
Bom.
Eu tinha mais cabelo.
Ele veio conversar comigo.
Eu lembro de você conversar comigo. Melhor que eu
Vai fazer mais de longe pegando os 4 painéis.
Vocês deram aula pra mim que não aposentarei.
2 minutos de diferença.
Eu posso falar pior. Ele foi pad.
Meu pad não chamava pad.
Sério, esse cara
Você fez também?
Tem aquele relógio lá.
Tem que ter aviso do tempo? Não falta.
Não, tô dizendo, não preciso do celular aqui, que tem aquele relógio.
Yeah. Hello, everybody. I will introduce our next speaker, Giselle. I'm very happy for this session specifically because, I mean, we are running FOSForums today, and we were able to make this joint session with the series of seminars that usually happens here at the Institute of Computing. So thank you very much, Professor Isleni. Giselle has been working with hardware design for quite some time, right, Giselle? Did high-performance graphical computers using Smalltalk, so you can see how long it is. And then he got back to USP to do his graduation course on chip design in the 80s. And in the 90s, he worked with the LSI department in USP, or LSI lab, actually, in USP. And then founded Merlin Tech to develop the children's computer around the new processor. He has a master's degree in ICMC at USP as well, right? And he has been doing work on advanced processor designs. In 2020, Giselle participated in Google's multi-project wafer, helping other groups to overcome some of the limitations on the tools that were used by then. And yeah, I mean, welcome, Giselle. It's really a pleasure to have you here.
Thank you. So this talk is going to be in English as part of FOSForums, but if you have any questions, you can ask in Portuguese and I'll repeat them in English. So this is just going to be a historical and a conceptual overview. I'm going to show some details, technical details, but very, very few technical details. Now, where do you start the history of chip design? I'm going to start at the beginning of the 19th century, where the battery was first evolved. So the 19th century started with, in the middle of the first industrial revolution, where the world was changing completely. It was now being powered by burning coal to generate steam to power things, or burning oil to generate light and heat. And so throughout the 19th century, I'm not going to go into these things. You probably have heard of all these people and their inventions. But electricity started to be more and more understood. I want to show one particular invention from the middle of that century, which is 1837, the relay was invented. And the important part, so if anybody doesn't know what a relay is, it's a magnetic coil that when you pass electricity through it, it will close or open an electrical switch, right? And what's important about it? So where does the name come from? If you have a relay race, then you have a bunch of athletes, and when one gets tired, he passes some kind of device, and he stops, and the other person continues. And that was the idea of the relay. So the relay here in the middle allows the sending station and the receiving station to be much further away than it would be possible until this point. So the key idea here, which is important for chip design, is that this is only possible because the inputs are of the same kind of thing as the outputs. So if you have a device that has, for example, the input is a mechanical rotation and the output is electricity, or the input is electricity, the output is light, you can't connect several of these devices. So here we have currents and voltages as the input and currents and voltages as the output. But the really important thing is there's a little battery inside the repeater, because it's important that the outputs be at least as strong or even stronger than the inputs. If the outputs are weaker, then you can connect 2 devices, 3 devices, then the 4th one won't work anymore. So once you have this, what that we call signal regeneration, that thanks to some external power source, then the outputs are actually stronger than the inputs, then there's no limit. We created, right after that, telegraph systems that were the size of continents. We were able to have the transatlantic cable sending things from North America to Europe. So this is important. If you want to build things without limits, then you need a component that has the same kinds of inputs and outputs, and the outputs must be stronger, right? So we had a bunch of, continuing in the 18th century, in the 19th century, we had a bunch of more inventions, but I want to show one in particular, which is called the Edison effect. Actually, several other people had discovered it before him, but normally the most famous person gets associated with a saying or an invention. That's just how life is. And he saw that when he tested his lamps, it would get discolored on one side, but not on the other one. And this is what we call thermionic emission. Because of the heat of the filaments, electrons were being ejected into the vacuum of the lamp. And because Edison didn't like alternating current, he used DC, then there was a positive voltage on one side of the filament and a negative on the other one. So the electrons would all flow and hit just one side of the lamp, right? In 1904, Fleming decided to use this effect to create a device we call a diode or a rectifier, where electricity would flow in one direction but not in the other one. And that's a fundamental electronic device. And it was improved by Lee De Forest. He put a third, and the diode had two groups of wires. One's called the cathode, the other one is the anode, and the electricity flows between them. And De Forest put a third, what he called a grid, between them. And then you could control how much current flowed. Not only can you control the direction of the flow, but you can control the magnitude of the flow. And that was important because the relay was amplifying digital signals. The relay, you turn on and off, and you could go to the other side of the continent like that through a series of relays. But when they wanted to do that for telephone, it wouldn't work because the telephone is an analog signal. You can't use relays for that. So this was essentially the beginning of electronics. And we had several semiconductor devices before that, but this device here, the carboroidum steel diode, it's what we call silicon carbide these days, it's a material, was the first robust one that could be manufactured. Before, we used what we call cat whisker, where you'd have a little crystal, like selenium or gallium, and then you'd have a very delicate little wire, and then you'd touch it, and that would rectify a signal, so you could have a radio. But you couldn't amplify it, so you had to have a little earpiece to hear it. But they were very fragile. I mean, this wire, as soon as you moved anything, it'd break. So this guy created a more robust. But what's the problem with building electronics out of valves or vacuum tubes? So those are two different names. Well, there's an interesting video on YouTube where a guy creates his own vacuum tubes in his home. And it takes him a whole day to make one vacuum tube. It's very complicated. You have all these little metal pieces. You have to put them together like that. You have to solder them. Then you have to heat the glass and you have to change it. So here's the final product. So this is a very, very complicated thing. And then they put several of these valves into a device, like for example, a radio. And that was complicated. So it doesn't look very complicated, does it? Well, look underneath it. So that's what it looks like underneath. This is what we call point-to-point soldering, right? So for every device, so you have sockets for the valves, just like you had lamps. So since the valves evolved from lamps, then you put in a piece of aluminum like this. But underneath, then you have all the other components, which are capacitors and resistors. then you solder wire between them, right? So this was very, very intensive, very hard to do. So electronics was something for the elite. It was very expensive. And how did you do these electronic devices? How do you make them? An engineer would draw what we call a schematic. So it shows all the main devices. The round things here are the valves. There's transformers, there's a loudspeaker, there's some switches, capacitors, resistors, there's 2 batteries, right? And now this is a little bit complicated to use, so that's not what I would give somebody on the factory floor. I'd give them what I call a net list. A net list is a text, where each line of the text shows all the wire, all the pins. It's a list of pins that should be connected together through wires. And this is, they're the exact same information, okay? But the net list is much, much easier for somebody to follow in and to build the device. So these are the kind of information that if I wanted to have somebody buy the components, then would use what we call a BOM, or bill of materials, which for each device it says where, who manufactures it, how many do you need, how many capacitors, what kind of capacitors, and so on and so on. So this is also information that's mostly, it adds a little bit of information like who's the manufacturer, but mostly this is the same information as the schematic. And this will be important later when we try to do this not on paper but on computers. The computer, if it's the same kind of information, then the computer should generate it. We shouldn't have to manually do it. But like I said, this was very complicated. So the first step is people try to eliminate those wires, those point-to-point wires, right? So they started in 1904 already, but the first, what we call printed circuit boards, were actually used in the Second World War. So here's in the hand. So they had a ceramic substrate. They tried to print conductive ink, so on. There were several complications. In 1948, the US government published it so that commercial people could use it. And the first devices using printed circuit boards came out, radios, in 1952. And how do we make these printed circuit boards? Well, the very first you start out with a material, which can be phenolate or it can be fiberglass. There are several devices, several things. It's insulator. And it has a thin layer of copper that can be glued or some other scheme can be attached. So here they have copper either on one side or both sides. So this is what you get from the board manufacturer. And then one scheme that was initially used was what we call silkscreen, which is like how you print drawings on your t-shirts, right? So you have this silkscreen which has holes in it, and then you put in either ink or something else. So now you need a new kind of information. We had the schematic, we had the net list, the bill of materials. Now we have the layout, so this is a new thing. It's also a drawing. It's also the same information as the schematic, but basically this is what you have to put on the silk screen, right? And let me show you the evolution of that, because we had a technology since, I was talking about the 19th century. One thing that was developed in the 19th century was photography. And so why not use photography? So you can create a transparent thing with the drawing that you want, right? It's like a negative with a film. Then you cover the copper with what we call a photoresist. It's a material that changes its property when exposed to light. Obviously, you shouldn't do that in light, otherwise it'll be ruined. And then what you do is you expose the light through the photomask, and then you go through several chemical processes. And so finally you have only the photoresist where the light touched or where the light didn't reach. There are the two kinds of photoresist. And then you put it in acid. And that will, the acid part is the same thing if you do silkscreen. Now the great advantage of this over the silkscreen is that you can have very, very fine details. The silkscreen is limited by the threads crossing. Normally we use the actual tracks, we use this photomask scheme, but then if we have, for example, we can put the names of the components on the board, then we use silkscreen for that sometimes. At least the name stuck. I don't know if a current board is actually made with silkscreen, but normally when you describe the layers to make a printed circuit boards, you have a layer that's called the silkscreen, which is just informative parts. Now, the interesting thing here is this was all done by hand. I actually tried to find a picture of one alternative. When I was in high school, we actually used a nail polish. You know, nail polish is a brush, and we painted our drawing on the copper. And we used that instead of a photoresist, and then we put it in the acid. But to make those photomasks, a scheme that was popular was there's something called litrosets, where you put little letters, but it had litrosets with the pads for the connectors, for the chips, for the transistors, capacitors. Then you put that, and there was a very thin, it's like duct tape, but very, very thin, and then you just draw it on top of a plastic, and then you'd have the photomask. But this guy here, Joseph Gerber, he created a device here in the 50s where you could type in commands. Here's an example of the kinds of commands that you could type in, and it would plot that. And the advantage is that repeatable. As you typed it, say on a paper tape, the information, and then you could reuse it again and again. And to this day, if you want to make a printed circuit board, let's say in China, they will say, well, what are your Gerber files? This is what it is, Gerber files. So you send them for every layer. They're going to create a photomask. So initially it was a paper plotter, and he quickly created a photo plotter, which was a machine in a dark room. And instead of a pin, he had a little light that would convert your drawing into a photomask. Besides the Gerber files, you also have to send some files for their numerically controlled machines to make the holes and to cut the outline of the board. That's a different format, but you get the idea. So this is where the Gerber files come from. Now, here we were replacing the valves with transistors, which were so much more efficient, so much smaller. The first one is almost as ugly as the cat whisker thing, but soon they had other techniques, but they were also very complicated to make. Here's Philco. This was one of the first popular ones, this Philco surface barrier transistor. You had a little wafer of germanium, and then you'd have two jets, that like water jets, that would dig holes into each of the sides. And it shined a light through this liquid. And when you could see it from the other side, then you know that you had just the right thickness, and then you deposit material. So these were all very, very complicated things to make. Until in 1959, this guy here, he came up with what we call the planar process. And here's the patent. So he shows, you start out, so here's, how do you get these wafers? Well, you have this weird oven where you have melted silicon, and then you touch it with a tiny little piece of crystal. Then you start to pull it up. And it will create this huge cylinder of pure silicon. That's actually, people are used to thinking that molecules are something that's too tiny to see. Well, that's a molecule that's larger than a person. And then you sliced it into these very, very thin wafers, these discs. And so here he's showing how he could make a bunch of transistors. So instead of making them 3D, they were flat. So this was the planar process. This is what it looked like on top, from the side. And here's a wafer full of these little transistors. And then you'd cut them apart and put them in a package. So this could be automated. This could be done by machine. So it sped up the production quite a bit. And one reason why this was possible was because of the mechanical properties of silicon, because germanium is a better semiconductor. Semiconductor is a material that is not neither conductor nor an insulator. And it's actually an insulator unless if it's completely pure. But if you put some substances that we call doping, then it can conduct electricity. And germanium is much better as a semiconductor. But mechanically, it's not as nice as silicon. And the key invention that came right before the planar process was that they found out that you could expose it to oxygen in such a way, or water vapor, in such a way that you'd have a very, very thin layer, which is drawn here, the top of the layer, of silicon oxide, which is glass or quartz. And so that would be so you'd have this wafer and it'd be protected. And then you could use the same process for the printed circuit boards to expose it, put a photoresist. So we're going to look at that again later. But the main thing is that once people looked at this and saw all these transistors, they said, well, why don't we connect them? So that's what Robert Noyce, working at Fairchild, did. He sent the patent just a few months later. It was only approved in 1961, but it's from 1959. So here is a device that has 4 transistors in it, and they're connected. So after he makes the transistors using the planar process that they were already using to make, then he added a layer of aluminum, just like you have a layer of copper in the printed circuit board, and did the same thing so that you'd have only the tracks. And these weird squares around the corner is where you'd solder a tiny little gold wire into the pins, right? So this was and this is the first commercial integrated circuit. And here in Brazil, in 1971, or 10 years after that, Professor Zulfo at the EDA, Laboratório de Microeletrônica, from the University of São Paulo, made the first integrated circuit here in Brazil. In 2021, they were celebrating the 50th anniversary. So here's what it looks like in a wafer. Here's a single one of them, and then how it gets packaged, right? We've had integrated circuit technology in Brazil since 1971. Unfortunately, I'm not sure that today somebody can make such a chip. I think we've actually gone backwards. Now, if I'm using a photographic process, then why make a few big transistors? Why don't I make many, many, many tiny transistors and make a really complicated chip? That seems like an obvious idea. Well, there are physical limits. I mean, you can't make things that are smaller than the wavelengths of the light that you're shining on the photoresist. And if you use red light, it's almost 1 micron. If you use deep ultraviolet, it's 193 nanometers. So that's the limit. But there are other problems. What if when I'm making this, when I get to the blue layer, it's off by a little bit. So here it's off. These two designs are off by the same amount. You see that the big transistors still work, but I've ruined all the little transistors. So imagine that this is a 10 micron transistor. This is a 100 nanometer transistor or something like that. So that means that I'm limited by how good my machines are, how can they place stuff. And there's an even worse problem. Imagine that it's not completely clean. Imagine that I have these little weird particles. Well, they haven't ruined the big transistors, but most of the little transistors have gone bad. So you have to make not only better and better machines, you have to make rooms that are cleaner and cleaner. So that's what's limiting you. But interestingly enough, in 1965, another guy from Fairchild that also went on to co-found Intel, Gordon Moore, he published a paper where he plotted the number of transistors in a typical chip up to 1965, not many, right? But he plotted it on a log scale. And he noticed that you were getting twice as many transistors every year. And then he later revised that to every 1.5 years. So that became known as Moore's Law. And why is that? Well, because they were buying machines that could position the wafer more precisely. They were making better optics for projecting the mask. So this is a commercial law, not a scientific law. It means that if you're willing to learn, spend time to spend money, right, then you can get better and better and smaller and smaller and smaller transistors. Now that means that if you arrive later, it's harder to compete. I mean, a factory in the 70s would have cost you $100,000 to build. A factory state-of-the-art factory in 2025 is about $10 billion because it has all this accumulated learning. Now, if you make these smaller transistors, are they going to be usable? Well, for several different kinds of transistors, they will get much worse, so that you can't really make them smaller. But fortunately, there's a kind of transistor called metal oxide silicon, or MOSFET. And a guy from IBM, Robert Dennard, observed that if you shrink everything by S, then all of the interesting features get better. The resistance doesn't change, but how fast you can switch goes up. The power that it requires goes down by the square of the scaling. So he figured out that the tiny MOS transistors would be much better than the big MOS transistors for designing a chip. So these two combined is what gave us the world that we have today of these fancy electronics. So here I'm going to start talking about open source tools. Several universities created a bunch of interesting programs, but I'm going to focus on the University of California, Berkeley. And there was an interesting circuit simulator called CANCER. It had a weird acronym, but it was limited. It had been paid for by the military, and so it was limited. It wasn't open to the public. So this Lawrence Nagel made an improved version of it using the Fortran programming language. And you would read a file like the one above. So you start with a kind of a net list where you give a component name, then what nets connect, you can use numbers for the nets, and what features. And then you have a bunch of commands, always starting with dot. So here he's doing what is called a transient analysis. How the circuit, when you turn it on, how it varies over time. You can do an AC analysis, DC analysis, and then you can plot. And this program called SPICE is still the backbone of the chip industry today. Okay? It was improved by another guy in 1975. And actually this SPICE 2, when I was working at the computer center at the University of São Paulo in 1982, I was given a listing of SPICE 2 and asked to port it from the PDP-11 computer to the Burroughs 6900 computer that was the university had. But I noticed from the comments that the PDP-11 wasn't the original version. They had actually been ported from a mainframe. So I said, well, I'm going to basically have to undo everything that they did to go from the CBC 6600 to the PDP-11. I'm going to have to undo it. So why don't you get me the CDC listing of SPICE and then I'll port it. I'm still waiting. They haven't delivered that yet. So, and actually, that would be a little bit useless because SPICE 3 from 1989 was completely translated to C. So that Fortran version, not very interesting. But in 1983, there was a very interesting tool called Magic, which allowed you to graphically draw your integrated circuit layout. Remember that we talked about the layout. And it had very interesting features, one of which was that it continuously checked a bunch of design rules. So that's what we call DRC, design rule check. So in order to make, let me go back here. In order to avoid all these problems, if you try to make a chip, a factory will say, oh, please never make this blue line thinner than this. Never have the red and the blue line be closer than this without actually touching. So there are a bunch of rules. We call them the design. And the idea is that if you violate these rules, your chip probably won't work. Whereas if you follow every rule, then it probably will. Not necessarily. And Magic would check the rules as you were drawing, so you always knew that you had a valid chip. Besides design rule checking, there's something called ERC, electric rule checking. It will check whether a transistor, for example, is only connected on one side, not the other side. If a circuit, every single circuit is connected to ground, into the power supply, and so on and so on. So that's ERC. That's a different thing. And now, you could use SPICE to simulate whatever design you create in Magic, and we still do, but that's really, really slow. So, because SPICE is an analog circuit, it creates a huge matrix and then it does integration and creates all the waveforms. So there was the IRSyn tool that simulated each transistor as just a single perfect switch and a resistor connected in series. And then, so it was many, many times faster than SPICE. Here I'm going to a little detour. One thing that became popular at the end of the 70s and the beginning of the 80s was, well, it's so complicated to make all this layout. What if the factory were to make all of the layers except for the very last one, which is the aluminum connecting, the wires connecting everything else? What if the client only had to draw the wiring like this one or this one? Here's an example. Here's the wires connecting. So this became a gate array. And the gate array is possible because there are several universal gates. For example, the NAND gate or the NOR gate, that you can design everything using just that single gate, multiple copies of that single gate. For example, the very first integrated circuit that was used at a large scale was a 2 a chip that had 2 NOR gates, each one with 3 inputs. And that was used in the Apollo guidance computer that landed on the moon. And they had thousands and thousands of the exact same chip, 2 NOR gates. Then you just wired them, and you made the Apollo guidance computer out of 3 input NOR gates. You don't need anything else. So this is a technology. The way that would do it, they'd give us a paper drawing of this, and then you'd have a colored pen and you'd draw where you wanted the wires. Or if you didn't know enough about that, then you give them a schematic for a TTL version of your chip and pay one of their engineers to do this drawing for you. One reason why I wanted to have this detour is because we had a bunch of Brazilian chips in the 80s, and they were all manufactured by national semiconductors in the United States using this technology. So we had Micro Digital, Unitron, Talcom. We had a bunch of companies that had Brazilian chips, custom designed. And unfortunately, at the end of the 80s, when this technology went away, also we stopped making chips for our products in Brazil, designing them in Brazil. Now, this is how you make your mask, your chip masks. You had this huge sheet called the Rubylith that was a transparent sheet, and then had a red sheet on top of that. And then with a knife, you could cut it, and then peel off the red parts, leaving the transparent where you wanted. And initially, people drew that by hand, and you'd make it really big, and then use a photographic process to make the mask smaller so that it fit in your hand. So a company created, Calvin and Kalma created a company, and they created something called the digitizer. So it was a table where you could point to any point in the table and press a button, and it'd send the coordinates of that point to a computer or to a tape. So you could have a paper drawing and convert it into computer coordinates. In 1971, they combined this with Data General Nova, a mini computer, and some software. So that's what it looked like. So you'd have these people with this huge table, all inputting drawings into the computer, and now it could cut the Rubylith for you automatically, and later on, just like the Gerber files. So this graphics design system, or GDS, it was later expanded to 32 bits. That's called the GDS2. And the files for this machine is what you now have to send to TSMC if you want them to make your chip, or to Samsung or somebody. So that's what the GDS means. It's the files for this computer here shows the masks. And these companies they tend not to last very long, so I'm not going to go too much into this. Here was a inflection point in designing computer. So a professor at Caltech, Carver Mead, he said, well, we're wasting our time trying to get every little micron out of this chip. Maybe if we were more conservative, we'd have a bunch of advantages. We could teach it to people. And he explained this at a research center called Xerox PARC, Palo Alto Research Center. And Len Conway was there and said, well, let's create a method then. And they wrote a book, Introduction to VLSI Technology, that introduced several things that are the basis of how we design chips. So their idea was, instead of having specialized people who knew the transistor in every little curve, what if I have a system designer designing their own chip? So they created something that they called the stick figures. So you just showed how you want to connect your transistors together without worrying about the details. They created the scalable design rules. So they, instead of using the design rules of the manufacturer, they said, well, let's be conservative. So they elected one dimension that they called lambda. So you'd say, oh, lambda is 4 micron. And then every other dimension would be some multiple of lambda. And they designed it such that if you designed it with these conservative rules, then your chip could be made on several competing manufacturers. You weren't limited to one. And more, if you change lambda from 4 microns to 3 microns, so that all the drawings shrank, you're probably within the design rules of the next generation from those factories. So you can continue making them, you can scale them. As the factories get better, you don't have to redesign your chip. So in this lambda, so until then, everybody had weird names for their design processes, for their manufacturing process. So they'd call HCMOS 3, PMOS 4 plus, or something like that. But from then on, people started just saying what the lambda was. So they'd say, oh, this is a 2 micron technology. This is a 180 nanometer technology. This is a 28 nanometer technology. Below 28 nanometer, it became a marketing term, but this is where these terms, oh, it's a 2 micron, 180 nanometer technology comes from. It's the value of lambda. And what was interesting was, so can we teach this to students? And they also came up with the idea of these standard cells. And that's based on the Pareto rule. The Pareto rule says that 20% of your effort is responsible for 80% of your results. So any optimization, you should focus on those 20%. So for example, if there's a chip that only happens once, if there's a circuit that only shows up once in your design, and you make it 4 times smaller, the overall chip won't even notice the change. Whereas if there's a little block that gets repeated 8,000 times, if you make it 10% better, it's going to have a huge impact on your output. So they said, for the parts that are not critical, what if we use these huge margins? So they created huge transistors, not the minimal transistors. They made it so all the cells have the exact same height. So the way that you use them is you take all the logic gates in your schematic and just put their cells side by side. They just go side by side like this. And all of their power and all their ground get connected together. All of their transistors are the same distance apart and they are vertical. So this actually made it not only simple for people to design it, but also made it simple for later on in the 90s for people, for machines to design. So you could give a net list, and the machine would give you a little block that would be standard cells. So here they came up with a scheme for using email to design chips. So you'd send your masks as an attachment to an email, and the guy would receive it, would put them all together into these masks here, and then you'd receive, each mask would combine the designs from all the students. So here's one. Each little block here with the pins is a different student design. And then the chip would only be wired to your particular design. So here. And several interesting industries came out of this. One of the chips that was made this way was the basis of a company called Silicon Graphics that gave us 3D graphics that we have today. So here's how they did it. And just to give you an example, here's an ARM1 processor using much of the same philosophy. A guy that worked on that project with Lynn Conway, he later joined a company called VLSI Technology, where they made it available to a British company called Acorn to make their Acorn RISC machine, or ARM, which later became Advanced RISC machine. But here's what the different parts are. So they decided, well, the bulk of the block is the registers and the ALU part, right? So we'll design very, very carefully for one bit, and then we'll just copy it 32 times. So this is what we call a bit slice scheme. For the barrel shifter, if you try to do it as logic gates, it's going to be a huge, huge circuit. That's why no chips up to then actually use the barrel shifter. But if you do it at the transistor level or the switch level, then it's this cool little block where the transistors form these Barber poles dialog. And they also use standard cells for the parts that didn't matter very much. So you can see that they just put the standard cells. Okay, so new companies came out to exploit this new way of designing chips, with Conway. And the first two actually designed their own workstations, just like the Kalma and the other ones where you wouldn't buy a software to run your computer. You didn't have a computer that would run any of this software. So you'd buy this system. So here's a Daisy Logician workstation, for example. There was Valid Systems, and Mentor Graphics was the only one that said, oh no, a lot of people are already making machines that could run our software, so they selected one called Apollo workstations and had their Mentor Graphics software run on top of that. But you can see here, this one went bankrupt in 1990, this one these all got sold. And then we had this interesting, we had two very interesting companies. One was Jim Solomon's design automation. He was trying to develop CAD tools at a National Semiconductor. Then he said, well, why should National pay a lot of money and then Intel will pay a lot of money and everybody else is going to pay a lot of money when I could be an external company and they could be my clients and then they would share the cost. It would be so much cheaper. So he spun out National. And I mentioned the design rule check. So they expanded DRC to Dracula and created this software. But then they had a lot of troubles in the marketplace and they merged into a company called Cadence System in 1988. And a company that spun out of General Electric, it had a software called Socrates. So what Socrates did was you gave it a very complicated chip design in terms of switches, right? And it would apply a series of optimization rules. That's why they wanted to initially call it optimal systems. And they would give you a much smaller, faster circuit that would do the exact same thing that you wanted before. And they actually advertised this, and a company called Sun Microsystem invited them, said, "Oh, can we see a demo of this?" So they took a design that Sun had spent 6 months optimizing. It ran through their software. And then it was suddenly 30% smaller. And they said, well, how's it possible that in 5 minutes now you have a design that in 6 months we weren't able to get that? And so Synopsys optimized on transforming circuits from one form to another, more optimized. Eventually they became the key purveyors of synthesis software that we'll see a little bit later. So here's how you make a chip. I've shown a lot of, I've been dancing around it, but how do you actually make a chip? Well, at the top left, you can see what every single step is actually a bunch of sub-steps. So you have the wafer, you grow the oxide, you apply the photoresist, then you touch the mask, you expose it to UV light, and then you have to develop the photoresist, you have to wash away the part, And then finally, now you have a wafer which has oxide on some parts and no oxide in other parts. And then you can do a bunch of processes. Normally we use doping, where I can either put a liquid with phosphorus or boron on the surface and then put it in an oven at 1,400 degrees or something like that. And then it will diffuse into the silicon. So that's what we call diffusion. Or I can have a particle accelerator and throw these charged particles at high speed, and they'll penetrate that. Then I have to heat it up because they'll ruin the silicon structure. So that's a single step. And here are the actual steps to making a CMOS circuit, right? So you start, then you create what we call the in-well. Then we put the drains and sources. This is actually one step, another step, combine it. Then we deposit metal, aluminum. Then we etch the metal so that you only have the tracks left. There's a huge problem with that. This is what a chip like that looks like. Every step that I add, it becomes, so metal 2 becomes really, really, really weird. So that means that that's my limit. If I add one layer of metal, it's all uneven. Then I add a second layer, it's really, really uneven. There's no way I can have a third layer of metal. You know, that was the state of the art for a long, long time, until they came up with the idea of polishing the wafer between each metal layer. So you start here with a very uneven with metal layers, and then you polish it, right? Now you have two problems with that. This polishing mechanical, chemical process injects a lot of charges, static electricity. I mean, if you rub something, you get static electricity. So if you part way through building this, you have wires that eventually will be connected, but right now they're hanging in the middle of the air. So we call that an antenna. So when you start polishing it, that charge will go into that and burn it. So you have to protect the transistors from that process. And another thing is that if the metal is too far apart, when you try to polish it, then it will bend in the middle. So any time you have some space, you have to put little squares to fill in the space. So this tool was released in 2018. It's not a tool, it's actually a collection of tools. It was created as a DARPA project where they wanted to see if normal people could design chips. So they wanted to automate as much as possible. So you design your chip using a hardware description language called Verilog, which allows you to have netlist and behavioral components. And then, so you start at the top with your design.v, and then you'd get your results GDS here. And you get a report on the design rule check or whatever. Here's the current version has a graphical user interface. When I used it back in 2020, it was purely textual. So these are tools created by other people. So Yosys will take a Verilog file and create a different Verilog file according to a bunch of rules, and they're equivalent, but you've transformed it in some way. And one way is that you can give a library, and it will create a new Verilog that only uses that library as subcomponents. ABC will do the same thing as Socrates. Then floor planning and placement means that you now have these list of components. Well, where do they go? So that the wires between them are as short as possible. Some of the things I'm going to talk about later, but eventually you get to Verilog, the GDS using magic. And one thing is that this term is used a lot, RTL. It means register transfer level, and it is indeed a level, but it's also a design style. So the same term has two different meanings. And as a design style, it's a circuit where you have a bunch of registers, all using the exact same clock. Here are the same registers. I drew them twice because in order to not have these arrows all coming back. And this is the clock. And there's a bunch of combinational circuits between the outputs of the registers and the input of the registers. Well, if you design it like that, then you only have to worry about one thing. When the clock arrives, the data can't change sometime before, which is the setup time, nor sometime after, the hardware, the hold time, right? And there's a little delay for the output coming out. So we have what we call a static timing analysis, which will tell you, oh, you want to run this at 40 megahertz? Well, sorry, there's this path here that takes too many nanoseconds. You're not going to work. So it will look through all possible paths through this system, and will tell you which is the slowest one, and then you can either redesign it or you can run a slower clock or whatever. So this is only valid if you design it using the RTL style. And another thing that you have to do is you have to ensure that this clock is happens more or less at the same time in every corner of the chip. So that's what we call the clock tree synthesis, right? So the first thing you have to guarantee that the clock goes everywhere at the same time. So here's some other open source tools that Electric was a commercial chip design tool from the 80s, and then in the 90s, the programmer decided to retire, so he donated it to the Free Software Foundation. So now it's GNU Electric. So if you want to, I don't know anybody that's actually using that, but it is a tool that's available. There's another tool, sort of like OpenRoad, from university in France, Alliance Coriolis. Does it have another L? I don't remember. So here's what it looks like, has same functionality. There's Icarus Verilog, or iVerilog, depends on how. It's not very graphic, so I just am showing you a different tool, the GTK Wave, which shows the waveforms, which is the output of iVerilog. iVerilog will simulate. So if you have a Verilog design, then you can see if it's going to work or not and see what the values are. It's iVerilog. So it's very good for debugging designs. Verilator is a similar tool, but it will take your Verilog design and translate it into C++ that you can then compile and run. So it makes applications from Verilog. And then you can use libraries like SDL, which is a graphics and sound library. And then you can, for example, simulate a Game Boy. Write it in Verilog and see if the graphical user interface works or whatever. So we started out with the university free open source tools, Magic, Spice, whatever. These eventually became very, very expensive. The Synopsys, Cadence, Mentor graphics are worth about $16 billion per year in terms of revenue. But we're now getting more open source tools back. So it's kind of a pendulum. It comes and goes. So now if you want to design, except that you obviously need access to the design rules, what we call the PDK, the physical design kit, which will give you the rules, will give you a library of standard cells, will give you SPICE models and other things. And until recently, well, the Lennon-Conway rules were published, were open. But they were not exactly what the manufacturers actually used. It would work, but since the 90s, they kept secret. So the only way to get access to this PDK was to sign an NDA. And in 2020, Google said, oh, let's see if we can make an open source chip. And then they negotiated with a company in the United States called Skywater. They released their PDK. And since then, we've had a bunch of other PDKs that are available. So thank you for paying attention. I'm not going to talk about any of this other stuff, which is equally interesting. We didn't have enough time. So, any questions that people? Sorry?
Would you say it's possible to grow a business in a country like Brazil, where we are a little bit behind, just based on open source software?
Well, the problem with using open source software and it's not the software, it's the PDK. The PDKs that have been released are for a very, very old technology. Now, there's a huge market for that because everybody focuses, oh, 3 nanometers because I want my iPhone, my whatever. But actually, the bulk of the chips are made using older processes. I mean, the Z80 process from 1976 was still being made last year. They stopped last year. So there is space for that. It's just not the glamorous part of it.
There's a company, it started out here from Von Braun Labs called, it's called Chip Inventor. They have their tooling available in the cloud, all based on open source design of chips. So they do all the workflow end to end. Even you get the PDK there, and then later press a button and send that to the phone. Made in Brazil.
Yeah, last year there was a talk about this event. But for educational use, it's great. I wouldn't use it commercially because I don't want my design to be on their computer in the cloud. But for educational use, I can't. It's actually better because it's really hard to make all these tools to install and make all these tools work on your local computer. So what they're doing is a fabulous job. It's really important for the educational market. So that's an example of what space there is for that kind of thing. Because any other question?
Do you think that the commercial, very expensive tools could represent any advantage against the open source tools?
Yeah. The Open Road was a bunch of scripts in a language called TCL, tool control language, that started out in Magic. These called a bunch of Python scripts that then called a bunch of C++ programs. Some of the boxes that weren't labeled were, like OpenTitan is the one that does the placement, the routing, or whatever. And so these are a bunch of student projects thrown together, and it works, but it's not as clean as something that you paid $500,000 for. You get the advantage. I don't see it as $500,000 worth of an advantage, but you do get an advantage out of the commercial tool.
Well, I think last year we had a talk at FOSForums, guy presented from TCAT, right?
Yeah, KiCad. KiCad.
He was mentioning that this optimization portion in his project, and he was showcasing something. So he was using like 80% of the area, right? And he was saying that this was a good accomplishment using that tool. Right? And then, I was just thinking about, when I was working at IBM, I remember they talking about, we have 10 transistors of space. So that's the kind of optimization that, high profile companies doing state-of-the-art microchips are working today. So it depends on the use case, I suppose, right? Maybe for your use case, 80% is okay, but if you really want to go deep and do very advanced technology, I think the only way is to pay these proprietary tools, unfortunately, these days.
Yeah, there are features missing from. KiCad has come a long way. I've looked at it almost since the start, and one of the advantages is that there are no limits. There are tools that will give you a free version, but only if you only have 2 layers, only if it's so many by so many centimeters or whatever. Otherwise, you have to pay the $10,000 version, and I actually have compared them. But some of the very high-end tools that are very expensive, for example, they'll simulate the electromagnetic interference. So you know that, oh, this track here is generating this waveform. I mean, you can do this with open source tools, but you really have to know what you're doing. So it's not for everybody. Okay.
Okay, thank you.